So hi guys, today we'll be talking about Spark memory architecture and how memory is divided inside a JVM. Because whenever we submit a Spark code or a program, it runs inside the JVM in the executor using its own heap memory. Now since everything is running on this JVM, the size of this heap memory is very important. Let's say I set the size of the heap memory to be of 1 GB. Will I be able to utilize this 1 GB memory as a whole for my execution? And if your answer is yes, you're wrong. Because life is unfair. Let's find out why. So let's start with Java heap memory. The memory is divided into three memory segments: reserve memory, user memory, and Spark memory. Now, before going into the details and intricacies of the memory allocation of all these memory segments, let's just first understand how we can set the Java heap memory. And the way we set it is using the configuration spark.executor.memory. And by default, it is 1 GIB. Now, it is a very technical term of saying 1 GB, but 1 GIB is equal to 1024 MIB. Now, this will cover into some other video like what is GIB, MIB, KIB. But for now, let's just focus on this. Let's start with the first memory segment, which is reserved memory. Now, Spark reserves a portion of the heap memory for storing internal objects and for JVM communication. Like how much memory has been reserved? 300 MB hard coded. Like be it 2 GB, 3 GB executor, 300 MB will be reserved for JVM communications. And when we reserve out of this Java heap 300 MB, the rest of the memory is called usable memory, which consists of these two memory segments, which is Spark memory and the user memory. What is user memory? Now it is mainly used to store the data needed for RDD conversion operations. Or we can even store our own data structures used in the transformation. The main thing about this memory segment is that Spark is unaware of it. Spark doesn't maintain this memory segment. So it has not been used for the actual execution. The Spark memory segment is the one which is actually used for Spark execution. So how we can define like how much of the usable memory has been allocated to Spark memory and how much portion of the usable memory has been allocated to user memory. Now this has been given by spark.memory.fraction. Now by default it is 60%, and these are the formulas. It says like 60% of the usable memory is been allocated to Spark memory, and the rest, which is 40% of the usable memory, is been allocated to user memory. So since we have all the defaults, let's see how much memory do we actually get for execution. I'll just quickly put it over here. What we'll do is we'll start with the usable memory because you have to find out, because 60% of the usable memory is actually the memory which you are going to get for Spark to execute, right? So usable memory is equal to our heap memory minus reserved memory. So our heap memory is 1024 MB minus 300 MB, which is reserved, which comes out to be 724 MB. So our usable memory is 724 MB. And then our Spark memory would be 60% of the usable memory. So Spark memory let's just open a calculator. I mean, it comes around 434, 435 something. into 0.6, 434.4. So this was all theory, right? Let's do some practicals. So let's try to, so we'll just run this session to create a, we'll just create a Spark session, and then we'll check the local host, and we'll go to the executors, and bingo, it's 434.4 MIV. See, we tested it out in practical as well. But let's play around with it. Let's say we don't want to get 60%, we want 75% of spark.memory.fraction. Like we want to give more memory for the execution. So instead of doing this, we'll do 0.75. So how much Spark memory do we actually get? So let's open calculator again. So this would be 724 into 0.75, 543. And let's set the spark.memory.fraction to 0.75. And the way we do it is, first we do have to stop the session. So we'll do spark.stop, and then we'll add one more config. Let's just bring this down, which is spark.memory.fraction, and we'll set it to 0.75. That's just done. And we'll reload this again. And we do get 543 MB. See? Again. That's all it is. So we'll go one step more into detail about the Spark memory, because it is not what we see, it is more to it. When we go inside the Spark memory block, there are more things. So let me just clear out this first. So let's clear out everything, and then let's just... So inside that Spark memory, we do have two blocks, which is execution memory and storage memory. So everything we cache or we persist some memory, those all are stored into storage memory, and execution memory is where execution happens. Now, there are two memory managers which are used in Spark, which is let's just go. Let's just come here and we'll come back to what were those formulas. So there are two memory managers which are there in Spark. First one is static memory manager, and the second one is unified memory manager. The difference between static and unified is, in static memory manager, if we go to the previous slide, I'll just remove everything. In this, the execution memory and the storage memory is constant or static. Like if we have defined, like in this Spark memory, if 75% of the Spark memory is execution memory and 25% is storage memory. So let's say I want to store something, but my storage memory is full and my execution memory is free. No one is using it, but still I won't be able to use that memory, and it can give me an OM error, right? So there is a disadvantage of that. While in unified memory manager, if in the similar situation, like I want to store something and the execution memory is free, I can use the execution memory. So there is this difference, but like how much of this execution memory and storage memory is there? Like how much portion of this is by default allocated? So the formulas are usable memory into spark.memory.fraction, which is the formula of Spark memory, into 1 minus spark.memory.storage fraction. So this spark.memory.storage fraction is the configuration used to set like how much memory is used for storage memory and how much memory is used for execution memory. And by default, it is 50%. So like 50% is given to execution, 50% of given to storage. And then memory managers, if it is static, then it will be 50-50 only. If it is unified, and if I want to store something and the execution memory is free, I can use the execution memory as much as I want, and vice versa. Like if I want to execute something and my execution memory is full and storage memory is free, I can use the storage memory for execution as well. The static memory manager was default before 1.6, and I don't think so it is no longer acting. uh, it has been removed, while the unified memory manager has been defaulted like 1.6 onwards, version 1.6 onwards. Now there are two scenarios which can happen inside this unified memory manager. The first scenario is when I want to store something and the execution memory is free and my storage memory is full, so I can use a part of a portion of execution memory. But when I use a part of execution memory and suddenly execution comes and knocks at my door like, I want my memory back, what happens? What we have to do in that scenario? So in this scenario, an eviction happens. So more preference is given to the execution memory. So in this case, what is happening is storage wanted to store something but it was full, so it asked like execution like, I'm taking some of your memory, which is this one, and just let me know when you want it back. So execution says like, hey, I want my memory back. At that time an eviction happens. An eviction means this memory which is taken by the storage has been freed up and then given back to execution memory. Simple as that. So this is the first scenario. There's also one more scenario. Can you guess? Let me just clear out this trace and then give me this. The second scenario is the other way, where the execution memory was full, so it took a portion of storage memory which was free at the time, and then storage memory comes and say, hey, you took my memory, I want it back. In this case, the storage memory has to wait. There is no eviction happens, the memory is not free on request, because execution memory says, hey, I'm executing right now, I can't give you this memory back, I'll give you, just give me some time. So it has to wait for the execution memory to perform its operations, and then it will free up and give it back to storage memory. There is also a third kind of situation where the storage memory is also full, the execution memory is also full, right? Like both is like tug of war, like I want more memory, I want more execution memory. In that case, there comes a situation of LRU cache where the memory is freed based on the LRU cache, LRU mechanism. So I hope you understood something out of this out of this video. And if you want to go into much more detail, like why there is 300 MB like reserved memory, or why the storage memory dot fraction is 0 0.6, you can go to the tickets of Spark. Like I'll show you some. So this one, which is Spark 12081, this is based on the unified memory management and like for the reserve memory, like why it is 300 MB. So earlier it was 250 MB, but they were getting OOM errors when running in local mode. So then they switched up to 300 MB. They saw like it is running fine with 300 MB, and they had two proposals, like first cut out 300 MB and then take 75% of what remains, or the second is use minimum of 75% of the JVM heap size, or JVM heap size minus 300 MB. And you might have noticed, like in this ticket, the spark.memory.fraction is 75%. And right now, when we were doing the calculation, it was 60%. So something might have happened, right? Like 75% to 60%. So that is also tuning. They tried every single thing, and whatever gives the best performance, uh, they change it to that value. So this was a ticket where they changed it to 300 MB. The one which I was saying, like it changed to 60%, that ticket is this one, which is Spark 15796. So in this, they changed it from 0.75 to 0.660%. And uh, it is mainly because of garbage collection. The ratio, the JVM garbage collection ratio is basically 2. So what it does, there are young generation, there are old generation. The size of the old generation was around 66%, but the execution memory, like the cache memory, was 75%, so it was not able to do. So it was slowing down because of the GC. We'll get into the more detail about this. We can make a separate video about it, about young generation, old generation, garbage collection. But if you want to go into detail, this is the ticket, which is Spark 15796. They have also tried different alternatives also, like they tried with 0.66, 0.63, and zero point 0.6 was giving them a more optimal solution, so they went out with 0.6. And this was 0.75, so it was taking a lot of time, GC time. And the last ticket which I want to share is Spark 26539. This is where they removed the memory manager, which was static memory manager, because after 1.6, unified memory manager is uh, defaulted. So to clean the code to look more representable, they removed this one. So I hope you like this video, and actually just give me ideas like what I can create, like what we can go through in the next video. So bye, have fun.